Welcome to this problem walkthrough. In today's session, we will tackle the problem titled Cutting Ribbons, which explores strategies to determine the optimal way to partition ribbons of various lengths. Stay tuned as we break down the approaches step by step and uncover the most efficient solution. In this problem, we are tasked with cutting ribbons into pieces of equal length. We are given an array ribbons, where each element represents the length of a ribbon, and an integer k, which specifies the exact number of ribbons we need. The goal is to determine the maximum possible length of these equal pieces such that we can produce exactly k ribbons. If it's not feasible to get exactly k ribbons of any length, we return 0. It's important to note that the ribbons must be cut into integer lengths, so fractional cuts are not allowed. For instance, a ribbon of length 9 can be cut into 3 ribbons of length 3, but not into 3 ribbons of length 2.5. This problem requires us to carefully balance how we divide the ribbons to meet the exact count of k while maximizing the length of each ribbon. Let's go through an example to better understand the problem. Suppose the input ribbons are 9, 7, 5, and k is 3. Here, we want exactly 3 ribbons of the same length. To achieve this, we can cut the ribbons as follows. The ribbon of length 9 can be cut into one ribbon of length 5 and a leftover piece of length 4. The ribbon of length 7 can also be cut into one ribbon of length 5 with a leftover piece of length 2. The ribbon of length 5 is already the desired length, so no cutting is needed. In total, we get exactly 3 ribbons of length 5. Since no greater length would allow us to produce exactly 3 ribbons, the output in this case is 5. Now consider another example. If the input ribbons are 7, 5, 9, and k is 4, we want exactly 4 ribbons of the same length. Here, the maximum possible length for the ribbons is 4. The ribbon of length 7 can be cut into one ribbon of length 4 and a leftover piece of length 3. The ribbon of length 5 can be cut into one ribbon of length 4 and a leftover piece of length 1. The ribbon of length 9 can be cut into 2 ribbons of length 4 and a leftover piece of length 1. In total, we get 4 ribbons of length 4. It's not possible to create 4 ribbons of any longer length, so the output is 4. Let's examine a scenario where it's impossible to meet the requirement. If the input ribbons are 5, 7, 9, and k is 22, we want 22 ribbons of the same length. Here, even if we try to cut the ribbons into the smallest possible size of 1, the total number of ribbons falls short. The ribbon of length 5 can be cut into 5 pieces of length 1, the ribbon of length 7 into 7 pieces, and the ribbon of length 9 into 9 pieces. Adding these together gives us a total of 21 ribbons, which is less than k equals 22. Since it's not possible to produce 22 ribbons of any length, the output in this case is 0. The problem also comes with several constraints and edge cases to consider. The length of the array ribbons can be as large as 10^5, and each ribbon's length can also go up to 10^5. Additionally, k can be as large as 10^9. This means the solution must be efficient, likely using a binary search approach to avoid timeouts. One edge case to consider is when k is greater than the total number of ribbons possible even at the smallest cut length of 1. In such cases, the answer is always 0. Another edge case involves scenarios with large ribbon lengths and k, where the solution needs to handle very high values while maintaining efficiency. Lastly, if there's only one ribbon in the array, the solution must ensure that it is cut correctly to maximize the length of the ribbons while meeting the exact count of k. To solve the cutting ribbons problem, we first consider a brute force approach. The idea here is simple: test every possible ribbon length, starting from 1, and determine how many ribbons of that length can be obtained. For each length, we sum up the number of ribbons we can create by dividing each ribbon in the array by the current length. If this total is at least k, then that ribbon length is valid. Among all valid lengths, we track the maximum value. However, this approach has a significant drawback. Since it iterates over all possible lengths up to the largest ribbon size and performs calculations for each, the time complexity becomes proportional to the product of the maximum ribbon length and the number of ribbons. For large inputs, this can be computationally expensive and impractical. This inefficiency leads us to explore an optimized approach, which leverages the structure of the problem to reduce unnecessary calculations. The optimized approach relies on a key observation: instead of testing all lengths linearly, we can treat this as a decision problem. Specifically, for a given ribbon length x, we can efficiently determine whether it's possible to cut at least k ribbons. If x is valid, then shorter lengths are irrelevant, and we should search for longer lengths. Conversely, if x is invalid, we must look at shorter lengths. This property allows us to use binary search, which systematically narrows down the search range. Using binary search, we start with a range of possible ribbon lengths from 1 to the maximum ribbon length. At each step, we calculate the midpoint of the range and check if cutting ribbons at that length produces enough pieces. If it does, we adjust the range to explore longer lengths, otherwise, we focus on shorter lengths. This strategy drastically reduces the number of lengths we need to check, making it much more efficient. At the end of the binary search process, the maximum valid length is stored in the upper bound of our search range. This approach has a time complexity of O log max_length for the search itself, and for each midpoint evaluation, we compute the total ribbons in O n. As a result, the overall complexity is O n log max_length, which is a significant improvement over the brute force method. Binary search is particularly well suited for this problem because it efficiently narrows the search space by leveraging the monotonic nature of the decision problem. While the brute force approach is easier to understand conceptually, it's computationally prohibitive for large inputs. Binary search, on the other hand, balances efficiency and scalability, making it the preferred solution. While it requires understanding the problem structure, its simplicity in implementation and dramatic performance gains make it the clear choice for solving this problem effectively. To solve the cutting ribbons problem, let's start by understanding the brute force approach. The goal is to determine the maximum possible ribbon length, denoted as x, such that we can cut at least k ribbons of this length from the given array of ribbon lengths. The brute force method involves testing every possible value of x, starting from 1 up to the maximum ribbon length in the array. For each candidate length x, we calculate the total number of ribbons that can be obtained by dividing each ribbon in the array by x. If the total is at least k, then x is considered a valid ribbon length. To implement this, we first initialize max_valid_length as 0 to keep track of the largest valid ribbon length found, and we identify the maximum ribbon length in the array, which serves as the upper limit for x during the iteration. Now, the algorithm systematically evaluates every possible ribbon length to determine the maximum valid value of x. We loop through all potential ribbon lengths from 1 to the maximum ribbon length in the array. For each candidate length x, we calculate the total number of ribbons that can be formed. This involves iterating through each ribbon in the array and dividing its length by x to determine how many pieces of size x can be obtained. These values are summed up into the total_ribbons counter. Once we have the total, we check if the number of ribbons is sufficient, meaning total_ribbons equals k. If this condition is met, we update max_valid_length to the current value of x. After evaluating all possible ribbon lengths, the algorithm returns max_valid_length as the result, which represents the largest ribbon length that satisfies the condition. The brute force approach ensures correctness but comes with a significant computational cost. For every candidate ribbon length x, we must iterate through the entire array, resulting in a time complexity of O n max_len, where n is the size of the array and max_len is the longest ribbon. This is because we perform a nested computation, looping over all possible ribbon lengths and for each, iterating through the ribbons to calculate total_ribbons. A key insight here is that the feasibility check, total_ribbons equals k, guarantees that every valid ribbon length is considered, ensuring we identify the maximum valid length. However, it's also crucial to handle edge cases, such as when k exceeds the total number of ribbons that can be formed, in which case the result should be 0. To optimize this approach, we can utilize binary search to narrow down the range of possible lengths. Instead of testing all values from 1 to max_len, binary search allows us to home in on the maximum valid x by reducing the search space logarithmically, achieving a more efficient time complexity of O n log max_len. Additionally, early stopping can be applied during the evaluation of total_ribbons, exiting the loop as soon as we confirm that k ribbons can be formed. This solution efficiently solves the cutting ribbons problem using binary search. The goal is to maximize the length of ribbons such that we can cut at least k pieces from the given set of ribbons. We start by defining a helper function can_cut, which checks if it's possible to cut at least k ribbons of a given length. This function iterates through the ribbons and counts how many pieces of the given length can be obtained by integer division. Next, we define the binary search boundaries. The smallest possible ribbon length is 1, and the largest is the maximum ribbon length in the input array. We also initialize result to 0 to store the best possible ribbon length. The binary search proceeds as follows. For each candidate length, mid, we use the can_cut function to determine if it's feasible to cut at least k ribbons of this length. If it is feasible, we update result to the current mid value and adjust the search range to explore longer ribbon lengths by moving the left boundary, left equals mid plus 1. Otherwise, we adjust the range to explore shorter lengths by moving the right boundary, right equals mid 1. The process continues until the search range is exhausted, ensuring that the optimal solution is found. Finally, we return the value of result, representing the maximum ribbon length that allows cutting at least k pieces. This approach ensures efficiency, with a time complexity of n*log, max_length, where n is the number of ribbons and max_length is the maximum ribbon length. Here, we start by defining the maxLength method, which is the core function to solve the cutting ribbons problem. The goal of the method is to determine the maximum possible length for ribbon pieces such that we can cut at least k pieces from the given array of ribbons. To achieve this, we use a binary search approach. First, we initialize left as 1, since the minimum possible length of a ribbon is 1, and right is the maximum value in the ribbons array, which we find using arrays.stream, ribbons.max.get as int. The result variable, initially set to 0, will store the maximum length of the pieces that meets the condition. Inside the while loop, we calculate the middle point, mid, and check if it is possible to cut at least k ribbon pieces of this length using the helper function can_cut. If it is possible, we update result to mid and adjust left to mid plus 1 to explore longer ribbon lengths. Otherwise, we shift right to mid 1 to try shorter lengths. This iterative process continues until left exceeds right, and finally, we return the result as the maximum achievable length. The can_cut helper function is designed to determine whether it is possible to cut at least k ribbon pieces of a given length. It takes the ribbons array, the target number of pieces k, and the desired length as inputs. Inside the function, we initialize a count variable to track the total number of pieces we can cut. Then, we iterate through each ribbon in the array, dividing its length by the desired piece length and adding the resulting number of pieces to count. If at any point count becomes greater than or equal to k, we immediately return true, as we have successfully met the condition. If the loop completes without reaching the required count, we return false. This early exit optimization ensures that the function runs efficiently, especially for larger inputs. In this example, we have ribbons of lengths 9, 7, and 5, and we need to cut at least 3 ribbons of the maximum possible length. To solve this, we use a binary search approach, starting by initializing 3 variables, left at 1, which represents the smallest possible ribbon length, right at 9, which is the length of the longest ribbon, and result at 0, which will store the maximum valid ribbon length we find. The binary search loop works by calculating the midpoint, mid, as left plus right, //2. We then check if we can cut at least 3 ribbons of this length. For the first iteration, mid is 5. We divide each ribbon length by 5 and sum up the results. 9 divided by 5 gives 1 ribbon, 7 divided by 5 gives 1 ribbon, and 5 divided by 5 gives 1 ribbon, for a total of 3 ribbons. Since this meets the requirement of at least 3 ribbons, we update result to 5 and narrow the search range by setting left to mid plus 1, which becomes 6. Now, in the second iteration, mid is calculated as 6 plus 9, //2, which equals 7. We check if we can cut ribbons of length 7. Dividing the ribbon lengths by 7, we get 1 ribbon from 9, 1 ribbon from 7, and 0 ribbons from 5, resulting in a total of 2 ribbons. Since this is less than the required 3 ribbons, we adjust the search range by setting right to mid 1, which becomes 6. In the third iteration, mid is calculated as 6 plus 6, //2, which equals 6. Checking this length, we divide each ribbon. 9 divided by 6 gives 1 ribbon, 7 divided by 6 gives 1 ribbon, and 5 divided by 6 gives 0 ribbons, for a total of 2 ribbons. Again, this is less than 3, so we set right to mid 1, which becomes 5. At this point, the binary search ends because left is greater than right. The maximum ribbon length that allows for at least 3 ribbons is stored in result, which is 5. In this second example, we have ribbons of lengths 5, 5, and 5, and we need at least 5 ribbons. The binary search starts with left initialized to 1, right to 5, and result to 0. For the first iteration, mid is calculated as 1 plus 5, / 2, which equals 3. Checking this length, dividing each ribbon by 3 gives 1 ribbon from each of the 3 ribbons, for a total of 3 ribbons. Since this is less than the required 5, we adjust the search range by setting right to mid 1, which becomes 2. Next, in the second iteration, mid is calculated as 1 plus 2, / 2, which equals 1. Dividing each ribbon by 1, we get 5 ribbons from each of the 3 ribbons, for a total of 15 ribbons. Since this is more than the required 5, we update result to 1 and set left to mid plus 1, which becomes 2. In the third iteration, mid is calculated as 2 plus 2, / 2, which equals 2. Dividing each ribbon by 2 gives 2 ribbons from each of the 3 ribbons, for a total of 6 ribbons. Since this meets the requirement, we update result to 2 and set left to mid plus 1, which becomes 3. The binary search ends, and the maximum ribbon length that allows for at least 5 ribbons is 2, stored in result. In this final example, we have ribbons of lengths 1, 2, 3, and 4, and we need at least 7 ribbons. The binary search begins with left set to 1, right to 4, and result to 0. For the first iteration, mid is calculated as 1 plus 4, / 2, which equals 2. Checking this length, dividing each ribbon by 2 gives 0 ribbons from the 1 length ribbon, 1 ribbon from the 2 length ribbon, 1 ribbon from the 3 length ribbon, and 2 ribbons from the 4 length ribbon, for a total of 4 ribbons. Since this is less than the required 7, we adjust the search range by setting right to mid 1, which becomes 1. In the second iteration, mid is calculated as 1 plus 1, / 2, which equals 1. Dividing each ribbon by 1, we get 1 ribbon from the 1 length ribbon, 2 ribbons from the 2 length ribbon, 3 ribbons from the 3 length ribbon, and 4 ribbons from the 4 length ribbon, for a total of 10 ribbons. Since this is more than the required 7, we update result to 1 and set left to mid plus 1, which becomes 2. The binary search ends, and the maximum ribbon length that allows for at least 7 ribbons is 1, stored in result. This approach demonstrates how binary search efficiently narrows down the possible values for the maximum ribbon length, ensuring an optimal solution in logarithmic time. The time complexity of the solution is primarily determined by the binary search process combined with the helper function can_cut. First, the binary search is performed over the range of possible ribbon lengths, from 1 to the maximum ribbon length in the input. Since binary search repeatedly halves the range, the number of iterations required is proportional to the logarithm of the maximum ribbon length, giving us O log max ribbons. Next, for each candidate length during the binary search, the helper function can_cut is used to count how many ribbons can be obtained. This function iterates through all ribbons, making its time complexity O, n, where n is the number of ribbons. When we combine these two steps, the binary search performs O log max ribbons iterations, and within each iteration, can_cut performs O n work. Therefore, the overall time complexity of the algorithm is O n log max ribbons. Now, turning to the space complexity, the solution primarily uses memory to store the input array of ribbons, which requires O n space. Beyond this, the algorithm uses a fixed number of variables, such as left, right, mid, and result, to control the binary search process. The helper function can_cut also does not allocate any additional memory beyond the input and the loops it uses. This means the additional memory usage is constant, or O1. As a result, the total space complexity of the algorithm is dominated by the input storage at O n, with no significant auxiliary space requirements. To understand the efficiency of the optimized approach, it's helpful to compare it to a brute force method. A naive solution would involve iterating through all possible ribbon lengths, from 1 to the maximum ribbon length, and for each possible length, checking if it's feasible to cut at least k ribbons. This would require O max ribbons iterations, and within each iteration, counting the ribbons would take O n time. The resulting time complexity for this brute force approach would be O, n asterisk max, ribbons, which grows much faster as the maximum ribbon length increases. In contrast, the optimized solution significantly reduces the number of ribbon length checks by using binary search. By leveraging the monotonic property of the problem, or if a length L is feasible, all shorter lengths are also feasible, the solution narrows the search space to O, log, max, ribbons, checks. Combined with O, n, work per check, the optimized approach achieves a much faster overall time complexity of O, n asterisk log, max, ribbons. Finally, analyzing the best, average, and worst cases of the algorithm gives us a clear understanding of its behavior. In the best case, the binary search quickly narrows down the maximum ribbon length within the first few iterations. However, even in this scenario, the time complexity remains O, n asterisk log, max, ribbons, due to the logarithmic search process and the need to iterate through the ribbons. On average, the algorithm performs a typical number of binary search iterations, proportional to log, max, ribbons, with each iteration requiring linear time O, n, to evaluate the ribbons, so the time complexity remains the same. In the worst case, the binary search completes all possible log, max, ribbons, iterations, and at each step, every ribbon is examined, leading to the same time complexity of O, n asterisk log, max, ribbons. Mathematically, the binary search repeatedly halves the search range, resulting in log, max, ribbons, iterations, and since each iteration requires O, n, work, the overall time complexity is confirmed to be O, n asterisk log, max, ribbons. The space complexity remains dominated by the input storage at O, n, with no additional memory usage beyond a constant amount for variables. When solving the cutting ribbons problem, there are a few common mistakes to watch out for. First, not considering edge cases can lead to incorrect outputs. For example, if the desired number of ribbons, k, is greater than the total sum of all ribbon lengths, the result is impossible, and this scenario must be explicitly handled. Another frequent error involves integer division. When calculating how many ribbons of length x can be obtained from a given ribbon, using floating point division instead of integer division can produce inaccurate results. Always use length / x to ensure you're working with whole numbers. Additionally, relying on an inefficient brute force approach can lead to time limit issues, especially for large inputs. Incrementing sequentially from x equals 1 to the maximum ribbon length is simply too slow. Binary search offers a much faster alternative. Finally, be mindful of input constraints. With values for k and ribbon lengths reaching up to 10 to the power of 5 and 10 to the power of 9 respectively, it's essential to test solutions against edge cases and large inputs. As you refine your approach, avoid premature optimization, ensure you understand the brute force logic before moving on to more advanced methods like binary search. Now, let's consider some insights that can help during interviews. One key takeaway is recognizing the underlying pattern in this problem. It's a variation of the maximum/minimum feasible value pattern. This class of problems is typically solved using binary search on the solution space, so identifying this early can guide you toward the right approach. Additionally, it's important to articulate the trade-offs between methods. For example, brute force has a time complexity of O, n asterisk max underscore length, which is significantly less efficient than binary search at O, n asterisk log, max underscore length. During an interview, discussing these complexities shows your understanding of the problem's scalability. Remember to emphasize edge cases as well, such as when k exceeds the total ribbon length or when all ribbons are of equal length. These are critical details interviewers often look for. Lastly, for broader context, this problem is related to several others, like LeetCode 410, 875, 1011, and 1482, all of which involve optimizing or dividing resources under constraints. Familiarity with these can deepen your understanding of the problem's structure. Finally, let's explore some alternative approaches to solving the problem. The brute force method involves iterating through all possible ribbon lengths and calculating the total number of ribbons for each length. While this approach is straightforward and easy to implement, it becomes impractical for large inputs due to its O, n asterisk max underscore length, time complexity. A more efficient method is binary search, where you search for the maximum feasible ribbon length within the valid range. For each candidate length x, you check whether it's possible to obtain at least k ribbons. This approach greatly reduces the computational cost, achieving O(n*log max_length, though it does require careful implementation to avoid off-by-one errors or missed edge cases. Lastly, there's the greedy approach, which involves sorting the ribbons and attempting to distribute them based on their lengths. While this method can be very fast, it's less flexible and may fail to handle generalized constraints, making it less reliable as a universal solution. Each approach has its strengths and weaknesses, so it's important to understand the problem requirements before deciding which to use. Thanks for staying with us through this problem walkthrough. We summarized the key points, highlighting the importance of balancing efficiency and simplicity when tackling algorithmic challenges. If you enjoyed this session, be sure to like, share, and subscribe for more coding tutorials. Until next time, happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!